My name's Dave Hughes. I'm the presenter of this HCC presentation in collaboration with Hitex about safety-focused networking on the AURIX family of processors. So the first thing I'd like to talk about is just the nature of functional safety. Functional safety, we keep seeing adverts for there's this tool and that tool that makes functional safety easy. Functional safety is just not easy. There's nothing easy about it. Back in the old days, last millennium, NASA did their space shuttle software, often regarded as some of the best software ever created. They reckon that it cost about $100 per line of code that they produced in that. Since then, many other attempts to assess the cost of producing high quality code designed for very reliable systems. And more recently, we've seen estimates from Greenhills on their integrity code that are way above $1,000 per line of code to produce very high quality, highly verified code. So when people say, I've got this and that tool that makes functional safety easy, this is just pure fiction. We have a phrase in English that if it looks too good to be true, then it probably is too good to be true. Functional safety is complex, it needs hard work. And one of the things is because it's complex, you need to focus on creating simple and as accurate a solution as possible, as focused a solution. Which neatly brings me on to the problems of trying to do networking in a safety environment. This diagram is not to show you what we do under safety. This is our general purpose network stack that we sell for embedded systems. It has got a huge number of components at the application layer, lots of applications, MQTT, FTP, Telnet, etc., etc. The transport layer with different security options like TLS, SSH, TCP, UDP, networking layer, lots of protocols again. There are thousands, literally thousands of RFCs covering different protocols and different protocol options that can be implemented in networking, and your data link layer, etc. And the one truism is that complexity is the enemy of safety. You need to create, obviously you need certain levels of complexity to achieve certain goals, but unnecessary complexity creates unnecessary cost. These costs just go up exponentially as you introduce layers of complexity to a design. So one of the important things is to be able to create an environment where you just focus on what's really needed to achieve your safety requirements of your product. So this webinar is going to be very much about how we produce software, networking software that we can use in a controlled way, in a very targeted way, and verify its consistency on the specific target, in this case, the AURIX family of microcontrollers. So I'm going to do some just general background. I'm not going to go into the details of different safety development processes. Basically, safety development processes end up with the same fundamental concept. It doesn't really matter whether you're in DO178C or for aerospace or 26262 for automotive, or 61508 for industrial. In the end, you have something that looks like a V model, and you can have different development methodologies. You can have Agile, you can have Scrum, you can do whatever you want in terms of these things. But in the end, you end up with something that looks like a V model. There is a concept moving across this diagram from left to right. You start with a concept, requirements, which is basically a specification, an architecture design, detail design. And then you have a verification phase, verifying the detailed design, the implementation, verifying the requirements, and then maintaining the operation and maintenance of the system. And yes, there are variations on it. Medical specifies slightly different to automotive to industrial. You have different fundamental safety considerations because in industrial functional safety, you want to just make something into a safe condition, which generally means switching it off. Stopping it operating. In an airplane, they can't just stop it operating. You have to go to a safe state, which doesn't actually switch everything off. In a car, you can't just launch all the airbags every time there's a minor fault on it. So you have different ways of handling safety situations. But from a software point of view, the way this is designed it has to follow something along this V model. And the key for me to all safety developments is traceability. The traceability from the specification, the requirement specification, through the design and implementation, your architectural design, detail design, and the test cases. The test cases that verify the design and the implementation, and the test cases that verify the specification. And for the highest levels of safety, you need a completeness of traceability. In other words, every element of the specification has a test case. Every test case has an element of specification. And likewise, the specification results in parts of the design and the implementation, and every part of the design and implementation is covered by a part of the specification and is covered by test cases. And this is how we guarantee the completeness and the maintainability of any particular safety system we're developing. You can do all the MC/DC testing you want, run all the test cases you want, but without some way of managing it and showing that the system is complete, you're not proving anything. You need to have the completeness. The completeness is guaranteed by the traceability of your processes. So we focus very much on 26262 for our networking stack, but because the methodologies from a software point of view are very similar, these can be very easily ported to other standards. One of the really nice things that we've picked up from 26262 is the concept of a safety element out of context, a SAOC. And sorry, run forward. And the whole idea of the safety element out of context is that if, for example, you're building a car, you don't design a microcontroller for a car. You have to take off-the-shelf components to integrate to a car. And so what you're doing there is you're taking something that wasn't developed in the context of the car and putting it into that context. It was developed out of context. In the same way, we can look at software. I mean, all the safety standards advise you to use proven software, but you have to make sure that proven software can work in your system. The whole history of software development, and indeed computer development, is building on previous libraries, things you've created before, and improving and building on top. Like your desktop PC starts with a processor, an operating system, you build up libraries on top of it. So the same concept applies, and you create libraries, and those could be considered as elements out of context. Safety elements out of context are just an extension of that library concept, where you have safety elements built around it to be able to validate that this will meet some kind of safety criteria. And so we're very much focused on the software SAOC part of that, which is to be able to create networking components, SAOCs, that we can integrate into safety environments because we build it with all the artifacts. And 26262 defines this process very accurately. This table here summarizes all the different parts of the 26262 specification that relates to building a SAOC, the things you have to do, because the 26262 is about designing a complete road vehicle from the beginning to the end. Only certain parts of that are directly relevant to creating a safety element out of context. And in this particular case, this is the software safety element out of context. So it's focused on section 6 of 26262, the software development at the software level and all the supporting processes. So one of the key parts of this is that there are sets of assumptions that need to be analyzed to decide whether this SAOC is going to work in your target environment. There are two sets of assumptions you need to consider. The first set of assumptions is the assumptions you assume when you create your SAOC, your networking component. We select that it's going to support TCPIP, it's going to do this RFC, that RFC, it's going to work on a big endian system, it's going to work with this OS. All the things that we assume we put into the software, we make a set of requirements for. The other set of requirements are the assumptions on the external design. In other words, we're going to run it. Can it run on a 32-bit processor? Can it run on a big endian, little endian system? How does it interface to the rest of the world? And these are the assumptions on the design external to the SAOC. And obviously, you need to make these two sets of assumptions becomes a complete set of SAOC requirements. And if you can make those requirements work in the context of your piece of safety software, in this case, our safe TCPIP stack, then we can work towards creating a functionally safe piece of networking software. But because of the complexity of the networking stack and all the options, we have to be a bit, things get a bit complicated because we don't want to settle for, well, you have to use the whole network stack always, and every time we add a new component to it, everybody has to use that. So what we do is we have a complete development process, which includes all our requirements specified indoors and our test cases specified indoors, and the two are mapped together, and then you trace that down into an architectural design, a detailed design, and different processes for doing the design, the implementation, the coding, checking the coding standards, etc. And so what we end up with is we have an overarching V model which covers the whole of all the networking sales, which specify an architecture and the assumptions of the whole design. But then we break it up into a whole set of individual V models for each component of the design. So for example, if you have a project that uses IP and UDP but doesn't use TCP, we have separate V models for each of the modules like UDP, TCP, IP, so you can just include the ones you need to by modifying the sets of assumptions of the overarching plan and then having the individual modules complete in themselves. So what we end up with is a networking stack which looks more like this. You have a set of components which each have their own V models, like the sockets, you have a V model, UDP, TCP. They all work with external components, like a timer is required for networking. Some kind of memory pool has to be handled for networking to be able to send and receive packets. An OS abstraction layer, there has to be some communication with the rest of the system. And so all these different components have their own V models, which we can maintain independently as part of a larger V model. And the thing that gives us is the flexibility to put different networking components together as is required for a particular target. So we're trying to minimize the amount of code, the amount of options, the amount of things we have to test by being able to create small bite-sized modules that we can put together to create a safety project. And you can't just regard that, okay, my project is complete in networking, because networking is dynamic. Things keep changing. People keep finding security flaws. To give you a very unusual example, if you look at the DNS protocol over the years, DNS was written, defined about, I think maybe 30, 35 years ago as a protocol. In the last years, in the last 10, 15 years, they've realized that there are weaknesses in the protocol. This wouldn't be a weakness in your design, your safety concept. This is a fundamental weakness in the protocols. There's a need to upgrade DNS implementations because of the weaknesses in the actual protocol design. Nowadays, there's a thing called DNSSEC that's available to replace it. Or you can just switch off certain options and how you handle the caching to avoid DNS poisoning issues. The point I'm trying to make is that networking, however you use it, is pretty well always going to be dynamic and needs the option of being able to modify it. But again, you can't take our whole suite of protocols and have them all available and modifiable. You have to work with some subset. So how we do this is we have a master cell, which is the BigV model, and within that we have a whole set of smaller cells that we put together, the IP cell, the TCP, the UDP, and we create individual instances for each project we work with customers on, so that for each one you can choose, okay, I only need IP and UDP, I've got their own change management. We supply all the artifacts from the requirements through to the test cases, working into the design, so that you get a complete project with that set of artifacts to be able to build a project with just the things you need for your particular implementation. So that if an issue comes along, be it with the protocol or because you need to add a feature, you can independently maintain your sale instance, independent from any other of your products or indeed any other company's products. This can be managed completely independently, each sale instance. So one of the essential points of how the 26262 specifies the safety element out of context is it defines exactly processes you need to go to integrate. So within this diagram, you have the item development. So this is in 26262, this is typically a road vehicle, a car. And you have the concept of it, and then you have the product development. And then in this, you will specify, we need to integrate a software sale, a networking component. So how do we do that? Well, what we do is we establish the validity of the assumptions. So the assumptions that the system makes, the item level, and there's the assumptions that the sale makes. And there's a process of doing a gap analysis and running change management. You can run change management on the car, you can run change management on the sale. And you keep modifying this and you modify this until the assumptions match. Obviously, you manage this through the V model of this sale, or the set of sales we put together for a networking product. We match them, and once we have a complete match, we can then merge this whole set of artifacts, the whole development process, the requirements through to the test cases, into the item under development. So that's the safety development system of the target vehicle in an automotive case, and you can then move forward with your product software development. So this is the sale concept. I think this is a very nice way of representing of looking at how you take a safety element out of context, in this case, a software safety element out of context, and merge it to the safety development process of an actual end manufacturer of the system. So having gone through this process, one of the key things to then be able to do is to validate that the thing we developed as a sale and validated on some other platform in some other environment, another world, actually runs identically or behaves properly when it's on the target system. To achieve this, we have created our integration test bench. And the aim of the integration test bench is to allow us to run the same test cases we run in development on the actual target binary running in the integrated target device. For this purpose, we have what we call our integration test bench, and we have the device under test. During development, often the device under test is just the application test running on the PC in its own environment, and uses maybe even the network stack of a standard desktop PC, or we put in another network stack and integrate with the Ethernet controllers. But once you get to the release phase, once we're talking about putting it on an actual target, then this device under test becomes our AURIX-based system on a target board, which we communicate with from the PC running the same test cases. And the way this works is that we have a thing called an RPC generator, which generates RPC handles for the test bench to use and for the device under test. And there's a communications channel between the two of them. The test cases are all written in C#, and there's a maintenance process for that, which I'll show you in a minute. And they sit within a framework, which is actually optional. It can talk directly to the RPC. The advantage of creating a framework is that if you create a framework for things like networking, you can use that then by porting the framework. You can use the same set of test cases on multiple networking stacks. And what we do is we build up our test cases. We build up our AutoSAR test cases. We built up our Open Alliance test cases for network stack. We run those identically on the Windows built-in TCPIP stack as we run them on the HCC, different HCC stacks. And that's because we create a framework and they can run transparent. And underneath the framework, there's also the lower test interface. And this is in the networking case, if you're running this type of software in the networking case, then this communicates over Ethernet with the device under test. And the point is the test cases are testing the instrument under test, which is our network stack in this particular case. And so this represents the test cases are working on the instrument under test. They do this by executing RPC calls over another communications channel. The one I'm going to demonstrate is USB communicating from the PC to the ShieldBuddysBuddy board, to the AURIX board. And the lower test interface is, of course, the Ethernet, where we're going to send Ethernet packets between the PC that we're using to validate it and the target device under test. So as mentioned, Hitex have a development board for working with the AURIX processors, the ShieldBuddy. This is there's a version for this for the TC275 and the TC375. HCC have developed a plugin module for this, which provides a couple of CAN interfaces, an SD card interface, and from the point of view of this presentation, an Ethernet interface. So you can just plug this into any of your TC275 or 375 ShieldBuddysBuddies and the ShieldBuddysBuddy into the ShieldBuddy, and you can then use that to test networking on this platform. We can also do this demonstration on standard Infineon dev boards, but obviously this particular demo is focused on the Hitex ShieldBuddy along with HCC's ShieldBuddysBuddy. So now I'd like to come on to try and demonstrate how the integrated test bench works. So we start off with the test bench. The test bench is a Visual Studio project. It contains a whole lot of test cases that we write in C#. And this is the interface and the list of test cases we have. The test bench then connects to the AURIX board, the ShieldBuddysBuddy, and on the target board we have a project which is built within using the Hitex tools so that's the Visual Studio project. I need to just show you the Hitex tools, which runs code on the target. And in this code on the target, we have quite a large project. It has all the networking stacks, but also to try and give you a quick demo that's a little bit more easier to conceive, we've also put a Tower of Hanoi problem solver onto the target software. I don't know if you all know the Tower of Hanoi problem. It's kind of a children's problem where you have 5 rings of different sizes, big to small, on 3 poles, and you have to move them, only moving on to bigger rings from the left-hand pole to the right-hand pole of 3. And so we've written a piece of code, a recursive code, to execute this on the target along with the network stack. And it recursively calls a moveDisk function. But within that moveDisk function, we've called the Hanoi change function, which is a callback to the system, which in this case we've put the callback to the RPC interface that then transfers a message relaying the state of the Hanoi rings back to the integrated test bench. So just to show how this actually executes, we've got this plugged into a live system. I can select from the list of tests here. These are our AutoSAR tests, which I'll show you a little bit in a minute. But we've also got these blinking LED tests, and there's a Tower of Hanoi test. If I execute this, you'll see a window pops up. This is a display window from our test cases written in C# that allows us to display. And this is the Tower of Hanoi running. Now, for those of you who've ever studied this problem, it's quite a simple problem to move the rings from the left side to the right side. The solution always takes 2 to the n minus 1 number of steps, where n is the number of rings. In this case, it's 5 rings. So 2 to the 5 is 32 minus 1 is 31. So there's 31 steps. And you can see that we ran this test bench, which from the PC to the AURIX system. The target code is the actual binary running on your target system. We haven't modified that. We haven't had to recompile that because we created these RPC interfaces. But it's able to relay the results back to the test bench, and every time it took a step, so we started, there was some initialization steps, and then from step 4, obviously we had 31 callbacks to step 34, where we returned the state of the Hanoi stack, and the test software was able to display that in the window you just saw. And then, of course, the tests are finished. So this kind of shows you how the running code on the target, by using what we call an RPC generator, we create these 2 interfaces on our test system, and we connect those together so that, going back to this diagram, we connect these RPCs together so that the test cases execute in C#, make an RPC call using the names of those functions and passing it parameters to execute the test, the Hanoi test, and it makes a callback to the RPC functions to say this is the state of these. And so the RPC generator that runs on the code, on the project code, generates a list of functions and their variables so that we can access these remotely without ever having to know details, the actual how to compile, link directly with the compiled code. And that allows us even to execute internal functions to the instrument under test, as well as just the standard API calls. We can actually look at individual variables or modify individual variables on the target using this method of creating these RPC files for managing a communication path between the test bench and the target. So this allows us to do on-target verification of the actual test cases we ran in development. So going quickly back to the test bench, as I mentioned before, we have all these AUTOSAR test cases. We also have a whole set of Open Alliance test cases and different stack test cases. So we can run these to test different features of the IP stack. So here I'm going to execute a AUTOSAR IPv4 test. You execute it. You can see that through the lower test interface, it's sent a packet, an ICMP packet. It gets a response back from it. And then the checking validates that that packet meets the test requirements. And once you've got a positive result, you get a green tick here. And so again, this is the binary of the code running on the target, being talked to through the RPC interface and through the lower test interface, the communications interface, in this case, Ethernet. And you can send packets to it, you can manipulate packets, you can get the results back, and you can validate that the test executed correctly, exactly on the target software that you have. And then because it's a safety software, in this particular case, we built this in a way that we don't accept fragmentation on this target device. So we can run our standard fragmentation test, for example. We run this test on this target. Again, we go through a whole set of execution tests. Because this was built without fragmentation to keep things simple and just assume that we're talking to something that doesn't want to do fragmentation and reduce the size of the code, this test failed. And so we get a test mark to say this has failed, and we need to either say, okay, that's part of the design that meets our design, or we need to reconstruct our test case, or we need to fix the actual target code and go back to development, go back into our whole maintenance process of traceability, finding out what's wrong in the requirements and the test cases and the implementation, and making the necessary modifications to pull that whole system together again. So this whole interface allows you to build up suites of test cases that you can execute with the given framework to achieve verification. So you keep a whole set of test cases for your project that you did during development. You execute the same one, you move the code onto the target, generate the RPC files for it, and you can execute those identical test cases in development on the binary you're going to use on target. This is how you can validate this stack. So I hope that gives you some idea of the whole process of trying to build networking software focused on safety for the AURIX environment. The whole thing is based, we based all our development of these components on the SAOC model, the safety element out of context model. And as you can see, the whole process, there's no single thing that you do to guarantee safety. It's a complete development process. The process you use is what keeps order. Without it, you cannot show safety and you cannot maintain safety. You can't make changes. So the core to everything is the process, maintaining it between all the way from the specification requirements through to the design, through the testing and back to the design. One of the really nice things about what we're presenting here is the ability to validate what was achieved, how your safety element out of context ran in development to validate that it behaves identically on your target. In real safety projects, even if you change the compiler version, companies don't like to change the version of compiler. It means that they've got behavior may change, timing may change it invalidates their test. They need to retest everything. Being able to validate again exactly that it behaves the same on your target is the final piece of a very complex puzzle that you're trying to solve in creating a reliable safety networking software, or any piece of software, because the same methods apply. So this is very different from pre-certified software, where it's been tested in some environment, in some configuration, on some endianness, on some compiler. And then you have to assume that when you put it on a different target, that everything runs identically. This is actually taking all your artifacts, moving them into your configuration, validating them on target in the configuration in which they're intended uses.